Good evening, everyone, and welcome to the 2020 Virtual Grand Canyon Star Party. I'm Ranger Raider Lane, the National Park Service coordinator for the event. And for 30 years running, Grand Canyon has been celebrating our pristine night skies through this annual Grand Canyon Star Party. Ordinarily, we invite hundreds of astronomers and thousands upon thousands of visitors to the park to enjoy 8 nights of some of the darkest and most pristine night skies in the United States. Each evening is kicked off with a special guest speaker in our theater, followed by telescope viewing, night sky photography workshops, constellation programs, and much, much more. Next year's Grand Canyon Star Party is June 5th through the 12th, 2021. So mark your calendars and cross your fingers. We hope to be celebrating that on site here at the park. This year, we are bringing you a taste of Grand Canyon Star Party in the virtual realm. We want to try to mirror how a night at Grand Canyon Star Party might unfold on site. So we're lucky to start each evening here from June 13th through the 20th, 2020, with one of our special guest speakers who are all willing to share their talks with us online this year. And we're excited to bring you some of the wonders of the summer sky into your homes with our virtual telescope viewing sessions that will premiere right after this program, so stay tuned for that. But before we introduce our special guest this evening, I have just a couple of entities the National Park Service would like to thank for their support in this event. First, I want to thank the Grand Canyon Conservancy. Now, they're the park's official nonprofit partner. They're doing all sorts of amazing things in the park. Some of their current priorities include trail restoration, the Desert View Intertribal Heritage Site, an amazing project unfolding at the Desert View Watchtower. They fund research and education in the park, and of course, one of their top priorities is night sky preservation. Through the generous support of Grand Canyon Conservancy and their supporters, Grand Canyon National Park was able to inventory over 5,000 lights in the park over the last few years and retrofit over 1,500 of those fixtures to become night sky friendly. We have plans to retrofit or change out many, many more as the years go on. And this has allowed us to become certified as an international dark sky park in 2019. This undoubtedly makes us one of the largest, most complex, highly visited international dark sky parks in the world. That very same year in 2019, the park was awarded the International Dark Sky Place of the Year by the International Dark Sky Association. And they're the nonprofit partner entity and partner that certifies parks and communities as international dark sky places, among many other tasks. In fact, their mission is to preserve and protect the nighttime environment and our heritage of dark skies through environmentally responsible outdoor lighting. We thank the International Dark Sky Association and their tremendous staff, and we hope they keep up the great work. Finally, Grand Canyon's International Dark Sky Place of the Year award could not have been achieved without the dedication, the passion, and the expertise of the Tucson Amateur Astronomy Association. They're our essential partner for putting on the Grand Canyon Star Party. In our virtual star party following this presentation, please thank the astronomers in the chat room. They do this out of pure love of the night skies, and the National Park Service is really proud to work with them in this endeavor. So with that, I want to introduce tonight's special guest speaker. Tonight, we are lucky to have Dr. Amber Strachan with us. She is an astrophysicist on the James Webb Space Telescope science team at NASA's Goddard Space Flight Center in Greenbelt, Maryland. She also serves as the Associate Director of the Astrophysics Science Division. Amber grew up in rural Arkansas and obtained her BS in Physics at the University of Arkansas in 2002 and completed her MS and PhD in Physics at Arizona State University in 2008. Amber is interested in answering questions about our universe that relate to how galaxies and their black holes change over time. In addition to research, Amber is very active in science communications. She frequently speaks at schools, astronomy clubs, museums, and research societies nationwide. Amber has done numerous live television interviews and media features for NASA and has appeared on CBS 60 Minutes, PBS Nova, the Discovery Channel, and the Science Channel. Well, tonight, Dr. Strachan will present Infant Galaxies to Alien Atmospheres, NASA's James Webb Space Telescope. Dr. Strachan, thank you so much for joining us tonight.
Great, thanks for that introduction. Thanks so much for having me. I did my PhD in Arizona, as you mentioned, and so I'm pretty sad that I can't actually be there with you all at the Grand Canyon. But I'm excited to be able to share share some of this with you online virtually. So just getting my little presentation set up here. Hopefully everything's good. So we're working on some really cool stuff at NASA, and I want to talk to you a little bit about some of that work that we're doing. One of the things I have always loved about astronomy since I was a kid is the fact that the questions that we ask in astronomy really get to the heart of what it means to be human. These big questions that we ask are more than just science questions. You know, they're questions about us as people, as humans on this earth. And one of the things I wanted to point out, and that I've recently sort of been thinking about, is the fact that these big questions, where do we come from? How did we get here? Are we alone? These questions all include that word we. And I think in general, science really strives to be an inclusive, where that we really does mean everybody. And I think it's important to acknowledge right now at this moment in our history of this country, the ongoing racial injustices that continue to persist. And the fact that we have a lot of work for us as a science community and us as a society to get to the we that we all really want. And I do believe it's possible. And I think one of the great things about NASA and about astronomy is that we can do hard things. And the Hubble Space Telescope, which is on the image here that you see, I think is a great example of one of the big, bold, difficult things that we did that has taught us an amazing amount about the universe. The Hubble Space Telescope has shown us unbelievable things about our entire universe, starting from our cosmic backyard of the solar system, extending all the way out into the further reaches of our universe. So this is an image of the Carina star-forming nebula, where you can see the entire range of starbirth, from stars being born inside dusty clouds all the way to the ends of stellar lives. And we know that when stars are born inside these dust clouds, they have these massive stellar winds that blow away the gas and the dust so that we can see the newborn stars inside. And when stars reach the end of their lives, they often will shed off their atmospheres in these beautiful displays like the one here, the Butterfly Nebula. And I think it's one of another really cool thing about astronomy is the fact that we're all connected. And these images show us that the iron in our blood and the calcium in our bones was forged inside of a star that shed off its layers into the universe, that was layer formed into other planets and ultimately into us. We're all connected in this beautiful universe of ours. And stepping out of the Milky Way galaxy, out further into the universe, of course, Hubble has also shown us an array of beautiful nearby galaxies like this one, the spiral galaxy M101. It is a nearby galaxy that if you could get outside our Milky Way and look back on it, our Milky Way galaxy probably looks a lot like this. And one of the really interesting things we've learned is that almost every big galaxy in the universe we think has a gigantic black hole at its center. We don't really know how they got very big, and that's one of the big mysteries that we have yet to solve. We know that galaxies aren't always stationary. Sometimes they come together and merge together in beautiful cosmic collisions like this, the Antenna Galaxy. And then galaxies, we know, don't just stand alone. They group together in groups and clusters. And of all the amazing Hubble images we've had, if I had to pick a favorite, this would be it. This is an image of the Hubble Ultra Deep Field. So in this image, Hubble stared at one tiny little piece of sky for about 11 days. And in this image, we see 10,000 galaxies. So this is a teeny tiny piece of sky, but every point of light you see here almost is an individual galaxy itself filled with hundreds of billions of stars. I think one of the things that Hubble has given us, one of the most important things, is just this knowledge that the universe is almost unfathomably huge. We now know, thanks to images like this from Hubble, that the universe has hundreds of billions of galaxies, perhaps even 1 trillion galaxies. So the Hubble Space Telescope, I believe, has really opened up the universe for us, and it has done amazing things in terms of our understanding of the universe over the past now 30 years that it's been in space. So this is an image of that Hubble Ultra Deep Field that I just showed you, but animated, like you're sort of flying through space. And so one of the great things about the telescope is we're able to learn, or not only look at these beautiful images of galaxies, but to learn what they're like. So these are real distances that we're able to learn from the Hubble Space Telescope. And what you see when you zoom through these deep images is that galaxies look different the further back we get. But even in the most deep images that Hubble has given us, at some point we've reached the edge of what we can see with Hubble. And so that means that we need a new telescope, one that is more powerful than Hubble. And that's what I want to spend the rest of this evening talking to you about. The James Webb Space Telescope is the scientific successor to the Hubble Space Telescope. And this is one of the major projects I work on at NASA. We're building the Webb telescope to really dig deeper and answer some of those big questions in astronomy that Hubble just can't quite get to. And we've made amazing progress on this telescope. It's been in the works for over 20 years, and we are going to be launching this telescope next year. So I want to talk a little bit about some of the big science goals that we have for Webb and some of the amazing things that we're going to be able to learn. So one of the key differences between Hubble and Webb is just the size. So the Hubble Space Telescope is about the size of a school bus. The Webb telescope stands almost 4 stories tall. So the mirror itself is about 7 times bigger than the Hubble mirror. And the size of a telescope's mirror is really important because it allows you to see both more detail in the images and it allows you just to collect more light. So one of the things that's going to make Webb so much more powerful is the size of the mirror. The Webb telescope will be by far the biggest telescope that we've ever sent into space. This is a model of the telescope. Of course, it's not the real thing because it's sitting outside here in this picture at NASA Goddard where I work. But you can see the major parts of the telescope here, the giant mirror and then the giant tennis court-sized sun shield that will protect the mirror from the heat and the light of the sun. So we're building this giant telescope to answer some of those very, very big questions in astronomy that we haven't been able to yet. So I want to talk a little bit about some of those big questions. So one of the first things we want to be able to do with Webb, or one of the main things, is really to learn about what's at the edge that Hubble hasn't seen yet, to see the very first stars and galaxies to be born after the Big Bang. We've never seen that part of the universe before, but with Webb, we'll be able to look back over 13.5 billion years to peer into the very, very early universe, to see it light up with the light of those first galaxies. We'll also be able to learn how galaxies grow over time. So this is another image of a galaxy merger. And we know that, again, galaxies in the distant universe look completely different than nearby galaxies. And we don't quite understand how that whole process of galaxy assembly happened. But with Webb, we'll be able to look at the universe in a new type of light, infrared light, and learn more about how that process happens. So really what we want to be able to do is to look at those very early galaxies in the early universe and figure out how we go from the little tiny clumpy galaxies to the giant massive galaxies in the nearby universe. Another thing we want to do with Webb is to see how stars and planets are born. So stars, of course, are the building block of galaxies, but there's a lot that we don't know about their birth. So stars are born inside dusty clouds. So this image from Hubble shows you an optical image, and the stars are born inside. So Hubble has a little bit of infrared capability, and you see the switch there from optical to infrared. And what that reveals is how infrared light can pierce through this dust to be able to see those stars being born inside. With Webb, we also will be able to do some amazing work into learning about exoplanets. So when I was a kid, we didn't know of any other planets that existed outside of our solar system. So thanks to telescopes like NASA's Kepler telescope and others, we have now learned that planets are everywhere. If you go outside tonight after this talk and look up at the sky, you point at any star in the night sky, and the chances are likely that that star has at least one planet. So we've learned just in recent years that the planets are literally everywhere. The universe, the Milky Way, is teeming with planets. So we've been able to find them by mainly using a method called a transit method. So we watch for stars. We watch for the planet to pass in front of the star, and that's called a transit. So we find this little dip in the light. And from this sort of simple observation, we're able to learn basic facts about the stars and the planets. So how big they are and how long it takes them to orbit their stars. But with Webb, we want to go the next step to learn much more about these planets. We want to watch the planet as it passes in front of its star. We'll watch the starlight as it filters through the planet's atmosphere. And from that, we'll be able to learn about what is in the atmospheres of these exoplanets. We'll be able to look at signatures like carbon dioxide and methane and water vapor. So in that sense, this telescope, the Webb telescope, is definitely our next big step on our search for habitable planets, planets that could host life. And for me as a scientist, I think that's one of the most exciting things that Webb will do. And this is extremely hard to do, which is one of the reasons that we've only been able to do it a little bit. So this is an image, a real NASA image of when Venus passed in front of the sun back several years ago. And so Venus, is relatively close to us, obviously, and Venus has this enormous, thick, giant atmosphere. But when you look at images like this, it's hard to see, right? You can barely see the atmosphere of Venus, if at all. So this image just demonstrates how hard this is. It requires really extreme precision and extreme technology to be able to do this. But with Webb, we're going to make a giant leap forward in our understanding of exoplanet atmospheres. So that's a summary of some of the science that we'll be able to do with Webb. This is just a drawing, an animation of the Webb telescope that has that iconic gold mirror, and again, that tennis court size sun shield. And then on the bottom there, what you see is the spacecraft bus that handles has the electronics, and then the solar panels come out from there, that sort of thing. So I'm super excited about the science that Webb is going to do. And I want to take you through a little bit of the engineering that's happened with the Webb telescope over the past many years. So this is an image of one of those gold hexagon mirrors. So the mirrors are coated in a very thin layer of gold. So the entire mirror is about 6.5 meters wide, about 21 feet wide, and it has a very thin layer of gold, about a golf ball's worth of gold spread out over that entire mirror. And engineering a telescope like this was incredibly difficult. And this is an image showing us assembling those mirrors one at a time onto this giant backplane structure of the Webb telescope. So all of this work was completed several years ago at NASA's Goddard Space Flight Center. We had to set up in a giant clean room, the world's largest clean room of its type, in order to accommodate this giant telescope. And so this video here shows us assembling the mirrors one by one onto this backplane structure here. And once that work was done, we got to see this amazing, incredible telescope with its giant golden mirror. Again, this was at NASA Goddard, so I got to actually go over and see the telescope myself, which was a really great day. It was amazing being able to look into those mirrors and know that those mirrors someday would be looking at the distant universe. It was sort of an existential experience. It was awesome. And so after that, the mirrors was assembled at Goddard. We started a whole barrage of tests. Of course, tests have been happening all along the way. Each individual mirror segment was individually tested before it was assembled. And then once we have the whole thing assembled, we do more tests on the mirror. The other big part of the telescope is the sun shield. And this video shows some early tests of unfolding the sun shield. So you can start to get a little bit of a sense of scale here for just how big this telescope is, because you can see the people doing the work here around the sun shield. So the sun shield has 5 different layers, and all of those layers have to be deployed in space. And so that is this is some of the tests that were done prior to the sun shield being assembled onto the mirror. So you've heard me mention TEST a lot during this talk. So we're going to put the Webb telescope out into deep space, about 1 million miles away. That's about 4 times further away than the moon. It has to be this far away so that it can get very, very, very cold, so it can see the infrared light from the distant universe. And the testing that goes into this whole telescope all along the way is critical because we can't go fix it. Humans have never been that far to space. And so we're building this telescope with a lot of tests built in all along the way to make sure that it withstands its launch and that it withstands its life out in the deep universe. This is just another image of one of those tests. We put these big tents over the telescope to move it from place to place so that it stays clean. And some of those tests include things like vibrational tests, shaking the telescope to make sure it will withstand the rigors of launch. And also things like acoustic tests, blasting the telescope with sound that will also create some of those vibrations that we'll sense during launch. We do cryogenic tests. We put the telescope in giant cryovac chambers. This is the one down at NASA Johnson in Houston, where the Apollo era spacecraft were tested to make sure that it will withstand the cold of deep space. So a lot of the work that's gone on this telescope in the past several years is all of this testing to make sure that it works like it's supposed to. This particular image here, it's not quite as high quality as the last few I've shown you, but this is the most recent image that NASA has released. This is an image of the sun shield and the mirror all put together. So the telescope is in one piece now. And it has recently undergone a deployment, so where the sun shield is fully out and then folded back up. So this is its stowed configuration. This is how the telescope will look once it gets into its rocket. So this is a pretty exciting image. And we have a few more tests to go over the course of the next year. Pretty soon, we will do some more vibration environmental tests of the whole telescope put together, sun shield and mirror. We'll shake it again, blast it with sound, and then we'll unfold it again to test it and to make sure all of those tests were successful. After that, we will put the telescope on a barge, and we will go down to South America, where the telescope will launch from French Guiana next year. So we're getting really close to launch, which is super exciting. And we're launching from French Guiana because this telescope is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. And the European Space Agency is providing the Ariane 5 rocket that we will launch on. So very exciting. We've got a lot of work left leading up to launch, but once we get down to French Guiana and launch the telescope, launch is really only the beginning. So I've mentioned how big this telescope is. It's so big that we have to fold it up like that in order to launch it. And then once we launch and it's in space, it starts to unfold. So it undergoes this really intricate unfolding origami type exercise where the telescope unfolds so that it can observe the universe. So what you've just seen in this video is one of the first things that happens is the communication antenna pops out so we can talk to the telescope. The solar panels unfurl soon after so that we can get power from the sun. And then we start this unfolding of the giant sun shield as well as the mirrors. So the sun shield itself is 5 layers so that heat is sort of dissipated between each of those layers so that once you get to the top of the telescope to where the mirrors are, that it is it's very cold, which is what we need to be. And so once the telescope unfolds completely, then we will start doing observations later on in the year. So it'll be several months after launch before we start to do regular science observations, about 6 months or so after launch. Because during that journey out to that distant part of space where Webb will live, it has to undergo this deployment, and then we have to turn on the instruments, we have to check out the mirror, lots of work to do before we have a fully functioning telescope. But I am so excited about both the engineering of this telescope. I think we've really pushed the limits of engineering of what we can do. And this is, again, the biggest and most complex telescope that NASA has ever attempted to send into space. And I think it will allow us to answer some of the biggest and most exciting questions in astronomy that I've talked some about tonight. For me as a scientist, I'm, obviously really excited about the work that we'll do, the questions we'll answer about the universe that we've already sort of planned out, some of the ones I've talked about tonight. We'll learn about exoplanets and about galaxies and black holes and even planets in our own solar system. We have these very set, detailed questions that we'll set out to answer, and I think we'll answer those. But for me as a scientist, I think that the most exciting prospect of telescopes like this are answering questions that we haven't even thought to ask yet. And every time we launch a big, bold mission like this into space, we learn things that completely surprise us. That happened with Hubble, it's happened with other telescopes, and I have no doubt that it will happen with Webb as well. So I hope you will follow along with us, with NASA, in this awesome journey of discovery. You can follow us on social media at NASA Webb. You can go to our website to learn more, which is given in the bottom here, JWST, James Webb Space Telescope.nasa.gov. Thank you so much for your time tonight, and please follow along and join us on this journey. Thank you.
Wow, well, thank you, Dr. Strawn. That was incredible, an incredibly exciting project. And like you say, it's projects like these that really, really just bring people together and unify us as a human race. And it's incredibly inspiring what you all are doing. I'm curious, for you as a scientist, as an astrophysicist, what role did pristine night skies play in sort of your upbringing to pursue these questions that you are currently trying to answer?
Yeah, great question. So I think you mentioned in the intro that I grew up in rural Arkansas, and we're talking very rural, middle of nowhere. I grew up in a tiny little town about 60 miles north of Little Rock. So Little Rock's not a huge city, but it was the biggest one close to me. And I had 28 kids in my graduating public school, high school class. So tiny little town, and it is absolutely fundamentally true that the reason I got interested in astronomy was because of that beautiful, dark, rural sky in my tiny little town in Arkansas. So, I often wonder if I would have grown up in a big city, if I would have had that same draw to be an astronomer. And I don't know, maybe, but it definitely was the dark sky that got me interested in astronomy as a very young kid.
Well, excellent. And, just following onto that, if we're moving our best and biggest telescopes out into space, is there still reason to protect and preserve night skies for observational astronomy, ground-based astronomy, I should say, as we move forward into the future?
Absolutely. So, I work for NASA, so I'm all about space. But there is still so much to do on the ground with ground-based astronomy. And I'm really grateful that I've been able to be to some of the most beautiful places on Earth to use ground-based telescopes like Chile and Hawaii. Mm-hmm. And so they're complementary. There's room for both, and there's a need for both, because the fact is that we need space astronomy to be able to get above the atmosphere. No matter how dark the sky is, there are some parts of light that we can't see at all from space. Like, for example, infrared light. There's parts of that infrared part of the spectrum can't see at all from the ground, no matter how clear the sky is. So we definitely need to get above the atmosphere for some of these observations. However, these big telescopes on the ground and even smaller telescopes on the ground really provide us with a lot of other advantages that we don't have in space. So, for example, if something breaks on a telescope on the ground, relatively easy to fix. Another thing is putting telescopes in space is expensive. It costs a lot more to put telescopes in space. And so telescopes on the ground comparatively are less expensive and easier to fix. So there's pros and cons for both. We need both in order to do good astronomy.
Well, excellent. And again, congratulations on the project so far. I'm sure everybody watching now will hopefully join NASA in following this project and seeing it to its completion. We're really excited to see some of the first images that come from this incredible project. And I wish you all the best in this and good luck. We're all rooting for you. Everybody online watching, again, please follow Dr. Strawn with the website she suggested, and hopefully we will be able to see all of you here on the virtual realm on site with us next year at 2021's Grand Canyon Star Party, June 5th through the 12th, and perhaps we might even see Dr. Strawn there, who knows. Let's keep our finger crossed we'll be able to celebrate on site next year. Dr. Strawn, thank you so much for joining us tonight.
You're welcome. Thank you so much for having me.